Okay, so we're going to do some complex analysis and we're going to find the minimum of the modulus of the exponential of z squared on the set D. And the set D is defined as the modulus of z is less than or equal to 1. So I've drawn that on the complex plane here. Basically it's just the unit circle of modulus 1, and it's the points all on the border and inside of D. And to find this minimum, we're going to use something called the minimum principal rule. So that's what we're going to use. So to do this, I'm just going to break the set D apart into two little bits. So the set D is made up of the interior of D, so that's all the points inside, and also, so a union of the border of D. So to write the border of D, I'm going to write this here. It looks like partial derivative. It's not a partial derivative, it's just a symbol what we can use for the border of D. So the very outside line. Okay, and for that, what we'll just call that is, we can call this D here. Now it's not conjugate of D, it just means it's every point in D including the border. So what can we say about all the different parts of this set here? Well, on the interior of D, we've got this function here for exponential of z squared. So let's just let f of z equals exponential of z squared. So this function on the interior of D we know is analytic and non-constant everywhere inside the interior of D. So that's first part of what we need to know for the minimum principal rule. The second part is that the border of D as well as the interior of D, the function here is continuous and non-zero. So exponential of z squared is never 0. So whatever value you put in there, minus 10 million or whatever, it gets close to 0 but never touches 0. So that's another important thing for using the minimum principal rule. So with those two things in place, what we can now say is the minimum, I'll just write this function out here, of the exponential, let's just write the set on it there, exponential of z squared on set D, just write that over there, okay, so there's going to be a point in there where this is equal to f of some value alpha. Now what that value of alpha is, we don't know there at the moment. So what is alpha? We need to look for alpha. Okay, so how are we going to find that? Well, the minimum principal rule states that the value is going to be found on the border of this D. So minimum value is found on the border of D. So how are we going to find that? So what we do know, there is a parametrization for the border of D. So what we can say is the border of D can be written as e to the I t, where t is in the set, let's just go inclusive from 0 to 2 pi, but not including 2 pi. So therefore we can keep going all the way around here, and that will give us our parametrization for the border. Okay, so now we know that, we can plug that in to our value here. So now what we can say is that this here, minimum exponential of z squared, we can say minimum exponential of z squared on the set D is equal to the minimum value, and all we're going to do now here is substitute in for the z squared because we know what the border of D is. So is the minimum of the exponential, okay, and now we're going to write this one in here. So it's e to the it, but we want it squared. So if we square this, we're just going to put a 2 in there. So e to the I 2t. Okay, and that is obviously true for the t in this range, and the z we know is in set D. So that's where this holds. Okay, so now what we're going to do now, we need to just break this apart a little bit. So if we just look at e to the I 2t and the exponential of it, so exponential of e to the I 2t. Now we know what this is equal to. There's an identity in complex analysis. So what we do know is that e to the z is equal to e to the real part of z. So z is in the form x plus iy. So therefore this is basically e to the x. Okay, now what is the z in Euler notation? So z equals cosine of theta plus I sine of theta. So basically the real part is cosine theta. So we can also say this is e to the cosine of theta. So that's something that's going to be important to us here when we're working out this. So exponential of e to the I 2t, using this law here, we can say that this is equal to the exponential. See, we don't need the modulus brackets anymore, of cosine. Now our theta here is just 2t. So it's the cosine of 2t. Okay, and again t obviously is in the range of this set. This is our parameters for t. This is our parameters for d. Okay, so with that in mind, basically what we're looking for now is the minimum value of this cosine 2t. So what's the minimum value of cosine 2t? So basically what we're looking for is the exponential of the minimum of cosine of 2t. Well, the minimum value of cosine is always going to be minus 1. So that's the exponential of minus 1, which is basically 1 over e. So that's our minimum value. What we need to know now is where that's going to be achieved. So basically what we want to know is where cosine of 2t equals minus 1. So where does cosine of 2t equal minus 1? Well, cosine of 2t equals minus 1 is achieved here at the point pi. So that's the point we're interested in. So basically if 2t equals pi, therefore t equals pi over 2. So therefore t equals pi over 2. And then looking at the set for t, it's in 0 to 2 pi, and 0 included but not 2 pi. So there might be another value in there. So if we plugged in 3 pi over 2, let's just write this down, 2 times 3 pi over 2, that equals, cancel that out, that equals 3 pi. Just leave it like that, cancel the 2's out, that equals 3 pi. But if we go around 3 pi, that's 2 pi and then back to there, so that's also the same point. So therefore we could have t equals 3 pi over 2 as well. So these are the points where 1 over e is attained for this function on the set D. T equals pi over 2 and t equals 3 pi over 2. So where is the value of this function attained on this complex graph here? We know that pi is here on this point, but that's not telling us where t is. So t is pi over 2, that's this point here. And if t is 3 pi over 2, that's this point here. So therefore, the minimum, so by the minimum principal rule, so by the minimum principal rule, let's just write that in properly, minimum principal rule, the minimum is attained, minimum is at plus or minus I. That's where it's attained. Okay, so using the minimum principal rule, we've worked out what the value of the t is when we plugged in our parametrization, and we now know that the minimum is attained at plus or minus I for this function. And plus or minus I, we know, is within the modulus of z is less than or equal to 1. So if I just write that in here, the modulus of I and the modulus of minus I, we know that both of these equal 1, and they are on the border of this set D here. There we go. Thank you very much.